Hello, I'm Frederick. Welcome all. I'd like to talk about vision AI systems, specifically more embedded vision systems, and what the fundamental building blocks are, what you need to do in order to be successful. A quick sort of introduction on why we at Framos feel that this is important. I found this figure which sort of predicts the growth that is expected globally in the AI-powered camera market. And you see that it's quite an exponential growth, quite impressive. That's sort of expected. And it's certainly because there are these huge advancements in compute power on the edge. Just like the other two speakers already mentioned, there is lots of compute power available. There were some recent claims that maybe there is some slowing down expected. There is Jensen Huang from NVIDIA claiming that maybe Moore's law is dead. There is, I think, different perspectives to that, but I think we all agree that we can still expect huge advancements in the compute power. And people are creative. They want to apply this compute power, and they think of AI-driven devices where they can really generate value by using AI models based on vision technology. Now, what does a typical embedded vision setup look like that sort of we are seeing in the market? It is consisting of sort of a central compute device, often SoC-based, which also has an image signal processor included. And then there are sort of optical sensor modules that are really sort of integrating directly and natively, often through the MIPI interface, into this central processing platform. Keep in mind, that's sort of the target platform that I have, that I use throughout this presentation. Now, in this talk, I'd like to highlight 4 of the main building blocks and their associated challenges when people like you want to design your next generation vision system. The first building block is certainly the image sensor. That's also where we come from at Framos. We are very good at understanding image sensors. And one of the typical challenges we see in the market is that people ask themselves, how can I truly sort of assess the image quality of the sensor itself? What are proper quality metrics that I can use to optimize my camera design? And I will speak about this later in the presentation. Another challenge is around the optics of the system. Typically, each image sensor is paired with a lens. And the question that we always see in the market is, how do I actually choose my lens subsystem such that I can truly maximize the image quality at the end? Another challenge which I will address in my presentation. There's a third one, the third main building block in any vision system, the image signal processor. It's usually a block in the SoC. Sometimes you can also do it yourself in FPGA, like we just learned. But typically, there is an existing pipeline that people would like to control in order to, well, tune the look and feel of the image and really make it suitable for the application. And the question is how to do that. Now, these are the 3 main building blocks, but I mentioned there's a fourth. And the fourth one is certainly, in my opinion, the most underrated one, especially when it comes to larger volumes, and that is production. How am I actually able to measure and maintain my quality, and at the end also my image quality, throughout larger production volumes? That's the fourth building block I'd like to address in my presentation. Let's start with the sensor. Sensor characteristics are sort of noise, sensitivity, dynamic range. There's a whole lot of different sensor characteristics. And typically, when people start, they look at the data sheet. They are intrigued by all the values they see, super low noise, super high sensitivity. They make their design of their camera, and they are, as you may see in the sort of the top picture, they are disappointed because they do see lots of noise. And this is where then typically you need to optimize. You need to optimize your electrical design, and there's a very powerful tool you can use, and that's the so-called EMVA 1288 standard that we also use internally when we do our design-ins. It's a standard which allows you to characterize sensor characteristics in a very standardized way, and with that you can truly understand how good your design is. I can only recommend, in case you do your own camera designs, that you really try to implement that standard in your daily operations. It will definitely improve your outcome. Second challenge that we hear, lens selection. Lens is, and I think typically people sort of often underestimate this, lens is an analog device. It's not digital. It's good or bad. You get all the gray values in between. And it truly depends also on the production quality of the lens itself. And so with a lens, there are so many things you need to watch out for when making the right selection. I sort of list out just a few basic ones. Certainly the image circle of the lens needs to match the sensor. Then also a very important one, the lens itself has a resolving power, and that needs to fundamentally match up with the pixel pitch of the sensor. If you get this wrong, your image performance will suffer, and it may even suffer dramatically. Then a lens also has an F number that typically controls not only the amount of light, but also the depth of field. So in case you have a depth of field sensitive application, something to pay attention to. A fourth one here, depth of focus, truly underestimated very, very often. So the lens itself is not always producing only a single sharp image plane where you then sort of position your sensor. Typically the wavefront of the lens, depending on the build quality, is sort of distorted. And you need to account for that when focusing, so when moving your image sensor to the right position to get a sharp image. And this needs to be taken into account when you do your assembly, and especially when you go to higher volumes, when you want to maintain a certain consistency throughout larger volumes. So that's definitely something you should have on your radar. And then the last one, there is also one fundamental characteristic, which is called chief ray angle, where a sensor has a certain chief ray angle and the lens. And in case they don't match up, I actually brought a nice image. You may see here in the projector that in the center of the image, you get some purple tint. So really, it's a color gradient. And that is because the coupling of the light rays into the photodiode of the pixel depends on where you are on the sensor. It is different in the center as compared to the outer pixels. And there, you may lose differentially different wavelengths, and that ultimately results into a color gradient, and it's almost impossible to really calibrate this out in post-processing. So these are some of the fundamental things you need to do when selecting your lens and pairing it with your sensor. There is a white paper we have, and also you can, of course, come to our booth anytime to learn more about how you best do that. This was the lens selection. There's the ISP, which I mentioned as a third building block. The ISP sort of converts the raw data, gray values coming from the sensor, into an image that is actually pleasant to our eyes. And if you don't do that well, you may get something like this. You do see some colors, so some color conversion has happened in debayering, but it doesn't look very crispy. There's maybe a green tint in this specific case, so it's not necessarily something you would like to show into the field to your customers. And that's why you need an ISP, and you need a proper ISP that can allow for different steps in the image pipeline. For instance, black level and defect correction. Then, of course, color reproduction, white balancing. I mean, really, we now list here 7, but actually there are pipelines that are even much more sophisticated than just these 7 steps. But you need to be able to really control, to a certain extent, all of these steps to truly get an output image that is somewhat pleasant to your eyes. And if you do that, if you really tune this properly, then you end up with something like this, which is, well, a lot more pleasant. You can feed this back into your central processor. You can start with your application development now based on this image and not based on something that looks bad. Image processing tuning is a little bit of an art even. I mean, at the end, it's all math. But since these ISPs are often closed and not really publicly documented, you need to work yourself around this, often by experimenting. But then also what is really a requirement is that you have a very good relationship with the provider of the ISP, and that's also where companies like Framos, but also others, can help to make this connection and truly get you the image that you need. Next use case, or next challenge, last challenge, production quality. So at the end, you select your sensor, you select your lens, you do your ISP tuning, you get a good-looking image, but this is only maybe for a single piece or 10 pieces. You like what you see, but you then need to ensure that you can reproduce this as higher volumes. Not sure what your application may require, maybe several hundreds, thousands. Some customers that we do business with even have hundreds of thousands. And there you need to ensure that you can maintain and monitor quality throughout larger batches. We do all our production in-house, and we are a vision-centric company. So we don't do general purpose system manufacturing. We only do vision-centric manufacturing. And in our production workflow, we measure the essential image quality characteristics for each piece. And what I show here is sort of a distribution of sharpness values for, I don't know, I think this was a 10,000 piece batch. You can see it's sort of a regular, normal Gaussian distribution, just as you would expect. There is production tolerances, but then together with our customers, we can sort of define cutoff criteria. What is considered good enough? What is considered not good enough? We can really nail this down. We do software-assisted production, so we have those characteristics measured for each device, and then we can really differentiate between OK and not OK. It will affect the yield, it will affect the cost, and we will always work with our customers to optimize this, but this is just a fundamental process you need to have in place in order to optimize your system performance. Now, these were the 4 big topics I wanted to show to you. I hope you found them valuable. What we did at Framos is that we sort of tried to productize all that into a family of camera modules, our so-called FSM Go. So what you see there is a platform. So again, we also take a modular approach, which I think today in this diversity of applications we see is the only viable approach you can actually take. But the way how this platform is sort of designed is that you can pick your sensor, you can pick different lenses, all of these are pre-qualified, you can pick different ISP tunings, and the manufacturing process is optimized in a way that you can, it doesn't matter whether you just order 1 piece or you order 10,000 pieces, it's all already streamlined to ensure that you get the product you need to be successful. And with that, my presentation ends. I'd like to thank you. I invite you over to our booth in Hall 10, right in the center. I think it's E54. We can continue with our discussions in case you have any questions. And very important, I was just now presenting an overview. We have four of my colleagues who are the true experts actually provide in-depth presentations of these topics that I mentioned here. So you please come to our booth and get registered and try to get a seat in one of these presentations. Very insightful. I can only invite you. And now thanks for your attention and your time.